So I will explain you briefly about the modeling part, how to model the geometry of the building, how to define the member section, and how to define the loads. Okay, and I will focus especially on the definition of the loads using VC 97 and ASCE 705 that for seismic and wind load. First, when you start modeling, you have to change the unit before you start a new model. You change the unit, normally we use kilometer meter unit, and then create new model in default EDV, and then you select grid only, and then OK. So you will have the grid, and you have to define the, and then you can edit the grid area according to your architectural drawings. So the first step is the definition of the grid system and the definition of the story data. Then you have to go to edit story data, edit story, and then you can insert the story if you have the 40-story building. If you want to insert, edit story data, insert story, and then you can specify the number of story. You can say 40. You will insert for 40 story. Then you can edit your story height. Edit story data, edit story height. You can edit the height. Okay. The height will be 3.1 or 3.2 meter. Then after you define the story height and grid data, you have to define the sections, frame sections, before you start the geometry. So first you have to define the material properties according to the design criteria that I gave you. And you have to take care about the material. You have to give the name. You have to give the mass per unit volume, weight per unit volume, and calculate the modulus of elasticity of the concrete, this concrete material based on the compressive strength of the concrete that you use. Then you have to specify the concrete strength here and the steel strength here, imposing steel here. If you have 2 or 3 types of concrete material, you have to define all the types. After you define the material properties, you have to define your frame sections and frame sections, slab sections, and wall sections. First, frame sections. You have to define by yourself for the rectangular beam. Just click at rectangular, and then you have to define the rectangular sections. If you have concrete material, if you want to use concrete material, just select concrete material and define the beams and column sections. If you use the flat slab system, you might not need the beams. You have to define only the columns. If you use beam and slab system, you have to define both beam and columns. One important thing is you have to specify this modifier here according to the crack section in the ACI 318. For the beams 0.35, for the columns 0.7, and for the shear walls 0.7, For the flat slab, 0.25. I think that one I explained you one time. These stiffness modifiers. So you have to specify these things in your frame definitions, and also if it is B, you have to specify you have to change this one to design as B, and specify the concrete cover to rebar center. This one you do not need to fill anything. This one is okay, 0, 0. This one is for nonlinear analysis. Okay, this is for B, and if you want to define for columns, you have to change the reinforcement column and put the rebar down. And reinforcement to be designed, not to be checked. You have to design that one. The program will give you the design reinforcement after you do it. After you define, so for the frame sections, it will be many section type. It depends on your structural system. Maybe for the columns you will have 10 or 20 sections. For the beams also 10, 20 sections. Then you have to define the, after you define the frame sections, you have to define the wall and slab section. For the wall and slab, you have to do not use plank. Okay, just use slab for the slab, and then use the concrete material and specify your slab thickness here. And in set modifier, you have to change the stiffness modifier. For the flat slab, you have to change M11, M22, and M12. But for the one-way slab, as beam and slab system, you do not need to change. If you use for example, if you use 150 millimeter thick slab, just specify 115 for both membrane and bending thickness. And always use shell element. Do not use membrane and plate. Okay. And for the wall, you can add the wall and define the concrete wall and specify the thickness of the wall. Let's say you use 0.4 for the millimeter wall. And use shell and set modifier, you just change F2 to O for the wall to 0.7. So after you define the walls and frames, you can start to draw your building geometry. If you want to draw the frame object, you can draw from this tool, and also for the column object you can use from this tool, and for the wall object you can use this one, and for the slab you have to use this one. Okay. I want to explain more detail on the load definition. After you draw the building geometry, you have to specify the load cases. You have to specify 5 load cases. The first one is the dead load. Dead load is for the surface of the building that you have. But you are not going to model the partition walls and other architectural dead loads. So you have to specify those loading as a superimposed dead load. So in your term project design criteria, we have mentioned the superimposed dead load separately. That superimposed dead load means the partition wall loading, and also the floor finishing loading, and ceiling and utilities loading. So those are we combine as the superimposed dead load. So you have to specify the superimposed dead load STL and specify as super dead. Okay. So dead load is just self-weight of the components that you model. Superimposed dead load is an additional dead load that you are not modeled. And light load, and then you have to specify the wind load and earthquake load. For wind load, you have to specify, you have to apply at least two directions. One is in X direction and one is in Y direction. Self-weight multiplier 1 means the program will calculate the weight of the components based weight of the components of the model and apply in this load case. Okay, I will explain you again. Here you define the material properties first, and then modify or show material, and you have the mass per unit volume and weight per unit volume. Okay, this is 24 kilonewton per meter cube. So this is the weight of this material, 24 kilonewton per meter cube, and then you define the frame section. This one, you use this material. So when you draw the one element, for example here, I will draw one element. So the program will calculate the weight of this beam by using the cross-sectional area of the beam, length of the beam, and it will get the volume and multiply with that material that you use. Okay, so you will get the weight of the member. That member weight will be considered in this load case. Okay, so if I use self-weight multiplier 2, for example, the program will calculate the weight of the entire building and then multiply with 2. So the building weight will be 2 times in this load case. Okay, but we normally do not multiply the factor of 2. If we want to use the load factor for the design, we define the load combination separately and use the load factor 1.2 dead load, 1.6 light load separately. But we never use change here. Okay, normally we use just 1. So in dead load case, if you use, okay, for example 0, the program will not consider the self weight of the components that you model in this load case. Okay, so there is no self weight. Normally we consider the self weight in the dead load case by applying factor of 1. So in dead load case, all the self weight is calculated. For example, here if you apply 1 again in live load, you apply the live loads separately in the building, like let's say 1.92 kilopascal for residential area, and in that case the program consider the dead load again in the live load case. So once you design the build for the member, for example for the beam, by the gravity load combination 1.2 dead load plus 1.6 live load. So in the for this scenario, for the dead load case, it consider the self weight 1 time. In live load case, also consider the self weight again. So you are considering the self weight 2 times in your design. So you have to consider only 1 time for the self weight in your load cases.
If you put 1 load,
so if you put 1 all, okay. For example, dead load 1, live weight 1, STL 1. So self-weight of the components will be calculated 3 times. Okay, so it looks like normally our gravity load combination is 1.3 dead load, and STL also considered as dead load. STL plus 1.6. So if you have self-weight multiplier 1, in this load case, it consider self-weight 1 time. STL you consider self-weight again, so this one also self-weight is considered. Plus the ceiling load, partition load. Okay, and live load also, if you use one, it is also considered self-weight. So in your load combination, you are considering the self-weight of that beam 3 times, which we do not consider. So you have to use self-weight multiplier only for one load case. Okay. So this is for gravity loading, and you have to specify the lateral load, wind, and seismic load. For wind, we apply at least 2 cases, wind X and wind Y. But it is not, you cannot say always wind X and wind Y. Better to consider what is the maximum area that your building is. If your building is like this, we consider X, consider Y, one time, consider X, one time, at least 2. Okay. But sometimes if the building area is diagonally, it is larger, so we should apply the diagonal direction as well. So I will apply the load case, wind case, and you have to select wind load. Okay. If you select wind load, after you select that one, self-weight multiplier 0, and then you have to specify the code that you want to use for the wind load. There are many codes in ETABS, but we are going to use ASCE 705. I prefer to use ASCE 7 loading rather than UBC 97 loading for wind load, because UBC 97 wind load has height limitation. You cannot apply UBC 97 loading for very tall buildings. Okay, ASCE 705 loading, and then after you apply, select that one, and then you have to modify the lateral load to import the parameters of the wind load according to ASCE 705. Okay, just click modify lateral load. Okay. Then you have to import the wind load parameters. There are 2 types of wind load application in ETABS. One is exposure from extents of rigid diagrams, and another one is exposure from area objects. Normally, when we calculate the wind load, we use the pressure coefficients, CP, in windward and leeward side. So, the first option is we just assign the diaphragms of the floor along throughout the height of the building, and the program will apply the loading based on that diaphragm dimension. Second is exposure from area object. That one is you have to draw the exterior walls of the building and then apply the pressure coefficient on that wall. That one is more complicated and more work. You have to draw not only the structure wall, you have to draw the exterior envelope of the building and apply the pressure coefficient for each element. So it is tedious and it can make mistake. If you apply the leeward and windward side different sign, positive, and if you make a mistake positive and negative in the pressure coefficient, the force will be wrong. So I suggest you to use exposure from rigid diaphragms. And 0 is the wind direction. 0 means X direction. Okay. If you change to 90 degree, it will be Y direction. Angle you can apply 45 degree, 30 degree. So I think it will be counterclockwise. To make it sure, okay, for example, you want to apply 25 degree wind direction. You can specify 25 and then run it and see the deformed shape of the building. This, for example, this is your building. You want to apply the wind in 25 degree this direction. You specify the wind locus 25 degree, and then from plan view you can see the deformed shape of the building. The building should move this direction. Okay. In case if the building is moving this direction, okay, with the sign plus and minus sign. So whenever you define the load case, after you analyze, check the deformation, displacement of deformed shape of the building, whether the load case is correct. Sometimes, for example, you want to define wind X and wind Y, but in another load case you forgot to change 90 degree. Okay, so you forgot to change this one to 90 and you use 0. So both load cases are for X direction. So after you analyze, when you see the deformed shape in plan, and in both cases the building is deforming only in X direction, so you have to correct that one. These are the common mistakes. And windward and leeward coefficient, that one is you have to calculate from the ASCE 7. Normally, CP value, windward coefficient is 0.8 always, but leeward coefficient, it depends on the building dimension. It varies according to the building dimension, like here you apply the wind this direction. So this one will be wind 1 is for 0.8, okay, and at the back E1 will be either 0.5 or less than that value. 0.5 is the maximum value for the leeward side. It can, if the building dimension is this one is shorter, this value will become, leeward side will become larger. But if the wind applies in this direction, okay, this one is wind 1 is 1. But if this one is longer, the leeward effect will be smaller. It will be less than 2.1. Okay. So you have to, in ASCE, this LYB ratio, based on LYB ratio, this leeward coefficient is varying. For if the plan is in square shape, okay, you just use 0.8, 0.5. But if it is rectangular, standard, you have to calculate the leeward coefficient. Another thing is application of the wind load. There are 4 cases in the SCE 7. Considering we are applying the wind load in x and x direction, 100% of the wind is just at the center, just at the center of the building, and also consider some eccentricity. We apply the wind load here. So these conditions will be considered if you consider all the cases. So if you want to calculate the wind load accurately, you just click all cases, and the typical eccentricity is 0.15, 15% eccentricity. So the program will automatically define the wind cases for those conditions. Then you have to specify the exposure height. In your TAP project, you do not have any basement. Your building starts from the ground level. So you just use the base, starting from base to the roof. But if you have the basement, you have to start the wind load calculation from the ground level, because under the basement it will not affect. And you have to specify the wind speed. Okay. Wind speed is not depending on the height. This wind speed is measured about 10 meters from the ground level. This is the standard, okay, not depending on the height. But wind pressure will vary on the height. Okay. But that pressure program will calculate automatically according to the code equations based on the wind speed that you use. This wind speed is 3 second gust wind speed. Miles per hour. Take care about the unit. And exposure type. Exposure type also I mentioned in the TAP project design criteria. If it is B, it is in the downtown. If it is D, it is near the sea. Okay. So B will be the wind effect will be small. And importance factor. Importance factor is always 1 because it is just residential building. Topographic factor, okay, just use 1. That topographic factor will be changed if your building is on the hill. Normally, our wind velocity profile is like this. This is the height. This is the speed. So we measure about this one. This profile is okay for the flat terrain. Okay? But if your building is on the hill, this is the flat terrain and this is the hill. Okay? So this profile will be increased. So to consider that effect, that topographic factor will be changed. Okay? This one depends on this height and also the length. In the ETABS it mentioned that one. Another one is the gas factor, to consider the increase in the wind response due to the dynamic effect of the dynamic behavior of the building. So in ETABS, the gas factor, default gas factor value is 0.85. But that one is for rigid building, like small building, one or less than 10-story building. Okay. The building has with a natural period of 1 second. You can use that one. But for the tall buildings, you have to calculate the gas factor according to equations mentioned in ASCE 705. There are many equations. Step by step, you have to calculate based on the natural period of the building. Okay. So you cannot add this factor in the model before you analyze. So you have to create your building model and then run one time for model analysis, and you will get a natural period of the building first mode, second mode. Normally our building response is first mode is X or Y translation, and second mode is also X and Y, and third mode is torsion. So for example, if your first mode is X direction translation, so you have to use that. For example, first mode natural period is 5 seconds. X. Second mode is 4.5 seconds. Y. So for wind X, you have to use 5 second natural period in calculation of gas factor. For wind Y, you have to use 4.5 second in calculation of gas factor. Okay. So this gas factor will not be 0.85. So if the building is 40-50-story building, it will be more than 1. Okay, 1.1, 1.2. Directional liquid factor, this 1 kD, this is normally 0.85. This one is not changing significantly. Okay, these important factors are gas factor. You have to calculate carefully. Okay. And same thing for wind Y. You have to specify wind Y, ESCE 705, and modify that load and change it to 90 and build the factors. After that, you have to define the earthquake loads. For earthquake loads, you have to define EQAs and EQY, like when EQAs, and select the quake. Okay. And you have to select the code that you want to use. Okay, UBC 97. Same thing, add new load, modify lateral load. Then you have to specify seismic loading. Here you cannot, for equivalent static loading, you cannot specify the direction in angle. You have only X and Y direction. In wind, you can specify the angle. Okay, for example, X direction, we will use X, and in UBC 97, the natural period calculation, for building natural period calculation, there is a simplified formula. That formula is based on the height of the building. So, but you have to mention the factor CT. That CT value is varying 0.35, sorry, 0.035, 0.02, and another one is 0.03 based on the structural system. That 0.035 is for steel building. If you have the shear walls, you have to use 0.02. So if you use ASCE 705, you have to go to, for the wind loading, you go to the wind loading factor and read the, for example, gas factor, read the gas factor calculation and calculate it. For and also CP coefficient you can get from the table of ASCE 705. For example, here CP value, I do not remember the table number. Some are already mentioned the figure number, but you can find easily for the CP value. And UBC 97, same thing. You have to go to earthquake section and see the parameters. This one for the shear wall building 0.02 and okay. Story range. Story range, your building is also your building is starting from the ground level, so you have to start from base to roof. But if you have the basement floors, you have to make your judgment whether you want to consider the mass of the basement floor in your seismic load calculation. Seismic load is coming from the mass of the building, not the external load. Wind is external load, but seismic load is inertia forces. Because of the ground shaking, due to its mass and acceleration, you are getting the inertial forces. So it is for the, if you have, for example, 6 basements, all basements will not be shaking during the earthquake because there is a surrounding soil. So the acceleration of those basement will not be will be negligible. And also in tall building, you will have the very thick foundation, like 3 meter, 4 meter thick net foundation. If you consider that mass in your earthquake loading, it will be very high because this 4 meter thick foundation mass multiplied with your acceleration, it will be very high. So normally people do not consider the basement mass in the seismic load calculation like wind. So just start from the ground level. But some people consider the mass of the basement in equivalent static load case, but not all. Maybe first 1 or 2 basement. It depends on the soil property. If your soil is very stiff and it can restrain the basement, okay, you can neglect. But if the top soil is very soft, so this basement might have acceleration, so you consider first 1 or 2 basement. It depends on the judgment. But some people do not consider the mass of the basement. Soil profile type, it depends on the geotechnical investigation. If the soil is hard rock, your amplification will be small. If your soil is soft rock, if the soil is very soft like clay, so it will amplify the ground shaking. So if you use, let's say, ST or ST, the seismic force will be increased. As you can see here, okay, SB, CA, okay, for this is the seismic zone factor. If it is zone 4, it is 0.4. Here, if you use hard soil, CACB is 0.4. If you use SC, it is increased 0.4 and 0.56. If you use, let's say, ST, it is increased further. Okay, 0.44, 0.64. So if your building is resting on the soft soil, your earthquake force will increase. And this one, it depends on, it's a near source factor. It is, if your building is located very near to the fault, we have to amplify the seismic forces again. If your building is far from the fault, let's say here, this is the near source factors, there is no amplification. If your building is very close, let's say within 5 kilometers, so the factor, the force is increased about 20%. Same thing, you have as wind loading, you have to specify the importance factor. Importance factor 1 is for residential building. I want to explain again for the R factor, for the seismic design concept. Okay. Here. And when you calculate the seismic force, you divide the force by the R factor, and you decide it. If we never design the building to remain elastic. If your building is not damaged, your building will remain elastic. This will be the base shear of the building, and this is the displacement, roof displacement of the building. So the building will remain elastic, and if after the loading, it will go back. It will go back to the uniform shape. Okay, there is no residual displacement. So if we design to remain elastic, the cost will be very high. We will have very big columns and walls. So we allow. The thing is, the earthquake that we design are for in the code design are for the design basis earthquake, which has 475 year return period approximately. So about 500 year return period earthquake, it can occur in 500 year, and if we design for elastic, it is not economical. So we allow some damage, but for 500 year return period earthquake, the building will have damage, but people should not be killed. So we reduce the earthquake force by the R factor. That R factor depends on the structural system. If you use the special moment resisting frame with a proper good detailing, so the building will, for example, the beam will yield, but it will be tactile. It will be tactile. It will not fall down like. This is so after this is the yielding moment. This is our design moment. Beyond that yielding moment, our beam will yield. Okay, and that's it. So under earthquake, we allow the yielding of the beams. So the force in the beam will reach this MY. Okay, and the beam start yielding. Beyond that MY, the force in the beam will not increase significantly, but it will deform. The rotation will increase significantly, but it should not fall suddenly. So to not fall suddenly, we have to provide good detailing, good confinement. So the beam will be like that. So it will not, if it is fall down suddenly, it will lose the gravity load carrying capacity for that member. So under it means that under earthquake, our members can sustain the large deformation, but not losing the gravity load carrying capacity. It will have large deformation, but it can still carry the gravity loads. So this is the seismic design procedure. So we have to, our members should have large deformation capacity. To get that one, we have to provide proper detailing, and the code allow us to reduce the seismic design forces by larger R value. If you have the brittle elements, brittle structural system, only and with a less redundancy, only the core wall, the code will not allow to reduce as much as special moment resisting frame. So R factor in the bearing wall will be 4.5. In SMRF it is 8.5. So we reduce the earthquake forces by R, but when we analyze the building with that parameter 8.5, we are running only linear analysis. We are not running the nonlinear analysis. So you in your model you are applying only this force, okay, and you will get this displacement only. But in reality, this displacement is not correct. Your building will deform more. So your displacement will be in the inelastic range. So, but you cannot get from the analysis directly because you are running linear analysis. So you have to estimate the inelastic displacement of the building by multiplying with the factors. This CD is for ESCE 7 earthquake. We get the, for example, you are in your linear analysis, you are getting the lateral displacement at the top 200 millimeter, for example, and then you have to multiply with the CD value, which is about 5. So it will be about 1000 millimeter. This will be the inelastic displacement. In UBC 97, you have to multiply back with R value. First, when you determine the design force, you divide by R value, but you have to scale back. When you calculate the displacement, you have to multiply back with R value. For example, we are using R equal to 8.5. When you calculate design free, this is the elastic free divided by, okay, you design for this shear. But when you design for, when you check for the displacement in elastic, you will get the displacement from the analysis and the multiply with R value in UBC, and UBC multiply again with one factor which is called 0.7. Okay, so from the analysis you have to multiply that with R and 0.7. The code assumes that this inelastic displacement and elastic displacement are same. The code assumes like that, but it reduced by some factor 0.7 or 0.6 in the code. Okay. So this is these are the factors that we use for the seismic design. Important factors are, okay, CD is in ASCD you estimate the displacement. Another thing is, okay, this omega naught. Omega naught is used in our design when we need to design the member to resist the maximum earthquake forces. That member should not fail first, should not yield first during the earthquake, like the transfer systems. If you have the transfer girder and some columns are resting on the girder, this girder should not fail first. This girder has to resist the maximum earthquake load that can occur in the system. So in that case, we have to multiply the forces with omega naught when we design. That omega naught value is approximately 2.8 in the code. So we will get the design forces and multiply with 2.8 for the members which are important in the transfer system. So after you define this one, the program will calculate the inelastic base shear. Okay, from inelastic base shear automatically it will calculate this one. Okay, you do not need to divide by R after analyzing. Okay. Then in UBC 97 there are some equations. There are 4 equations to calculate the base shear. That one we divide the base shear by R value, but there is a minimum requirement for the base shear. If even you reduce by R, but if the minimum base shear, design base shear equation is given, you have to use that equation. But the program automatically check those equations. You do not need to calculate manually. Okay? And another thing is, in those equations, the program used the natural period calculated from the simplified formula, not from the modal analysis. And then you have to define EQY and Y direction. After you define the load cases, and you have to apply the loading in the structure. There are, now we define 5 load cases: dead load and live load, STL, wind and earthquake. Wind and earthquake and dead load you do not need to apply in the model, because dead load is self-weight, it will automatically calculate it, and wind and earthquake also program will calculate automatically. Only STL and live load you need to apply in the model. Okay, so to apply that loading, you just need to select the floor areas, floor elements, and assign the loading. First you complete entire model and then select area object type, okay, and then floor, click OK. So it will select all the floors, and then you apply, assign shell area loads uniform. Okay. If you want to apply STL, then okay, 2 kN per meter square, just apply it, so it will apply. You can right click and check whether it is applied. This is 2 kN. And you can reselect all the floors and assign shell area loads uniform, and live load, let's say 1.92. After that, you have to define the mass source. This mass source will be used in calculation of your seismic loading. This is important. You have to, normally we use the second option. This first option is from self-specified masses. The program will calculate the mass only from the self-weight that you model and other additional mass that you assign. So if you select first option, the program will not consider the superimposed dead load, which is also acting as a permanent loading like the floor finishing, partition walls. So it will neglect those mass. And from loads, I prefer that one. We can specify the load cases that we want to consider as a mass. Normally we consider dead load, self-weight of the building, and superimposed dead load, 100% of the superimposed dead load, and some portion of the live load. Okay? But live load we do not consider 100%. We normally consider 25% of the live load. Okay? Because for example, we design for the common area 4.8 kilonewton per meter square for the live load. But this is for the gravity load design. This 4.1 in 1 meter square, 4.8 kilonewton will not exist in reality. So we estimate the actual live load will be 25% of the design live load. So we apply live, dead load, and superimposed dead load. But some engineers do not consider the live load at all. They consider only dead load and superimposed dead load. And some people consider dead load, superimposed dead load, and live load in the storage area only. They do not consider the live load in the residential area. It depends on the area. But our practice is consider all live load 25%. And this is the second option that I suggest you to use. And then include lateral mass only. So that one is to simplify the analysis, because normally our buildings, these mass is used for lateral load. So you can consider the lateral mass only. But if you want to check the floor vibration for the gravity load, you have to uncheck this one. So it will consider the vertical mass as well. Right? For the seismic load, include lateral mass only, and the lateral mass at story level. That one is the program will land the mass at story level, like for example, this is your story level, level 1, level 2, this is your shear wall. You have the mesh, and you mesh the floor wall between the level. This is elevation. So you have the nodes. If you land the mass at story level, this mass will be down to that level. So it simplifies the analysis. Otherwise, it will consider all the mass in the mass matrix. So mass matrix will be large. This one, if you land, the mass matrix will be small, but the accuracy will not be changed so much. You can land it. And if you use the third option, it is from self-specified mass and load. This one you have to take care. If you use the third one, the program considers the self-weight automatically in mass calculation. And you specify the dead load again, it will calculate again the mass. So the self-weight will be considered 2 times in mass calculation. Okay. So if you want to use this one, you have to delete this. Okay. But I suggest you to use second one and consider whatever the load is that you want to add. Because if you make mistake here, when you do the modal analysis, your natural period will be wrong. If you consider 2 times the self weight of the building, your natural period will become longer. Okay. So I have shown you about the static load cases. Okay, but you need to define the response spectrum cases for the seismic loading, because for the tall building we should not design using equivalent static analysis results, because the higher modes are significant. Dynamic behavior is not as simple as the small building. In small building, all the mass are participating in first mode, but in tall building, higher modes are also significant. When you run the modal analysis, you will see the modal participating mass ratios, and you can see in the first mode it will participate only 40-50% of the total mass. Other modes are also important. Other vibration modes are also important. So we have to run response spectrum analysis to consider the effect of other modes in your seismic design. First, you have to define the response spectrum function before you define the load case. The function can be imported from the like the equivalent static loading from the code. Here, define response spectrum function, and you can select which spectrum do you want to use. UBC 97 or ESC 7, whatever UBC 97. And then you have to specify the new function, and this function is generated according to UBC 97. Okay, but you have to fill the coefficient CACB value according to the code. So this CACB value you can check, okay, from the equivalent static analysis. Here, EQH, EQY, or a file level load, you can get this CACB value 0.44, 0.7. Okay. But this CACB value will be changed according to the soil type, seismic zone factor. Okay. If you change this one, okay, SP, it will change 0.004, 0.4, SP 0.4044, 0.64. So you have to note down this CACB value and import back in response spectrum function. Response spectrum function, modify show function 0.44, 0.64. Okay. After you change, function will be automatically updated. So program will calculate, and also this one, damping ratio. Damping, you have to use 5% damping for the concrete building. We use that one, but for the steel building, damping will be smaller. But anyway, you have to use 5% here, and the program will calculate the seismic forces based on this function. Here, okay, this graph, as you can see, this axis is natural period of the building, okay, and this y-axis is spectral acceleration of the building. Do not confuse with the ground acceleration. This acceleration is the acceleration of the structure, not the ground motion. So, for example, if your building is 50-story building, your natural period may be 5 seconds, 6 seconds. So you go there here. Okay, let's say this is about 5 seconds, and spectral acceleration is 0.12. Okay, so this 0.12 is multiplier of g. So it means that 0.12 g. Okay, so this is for, okay, for example, this is for first mode. The first mode spectral acceleration will be 0.12 g. And then if the building is a small building, that 100% of mass will participate in 0.12 g, and then you multiply with the mass of the building, you will get the base shear. This is the acceleration of the structure. So F equal to ma. So you multiply with your building mass, you will get the base shear, the design base shear of the building. But in tall building, the higher modes are also significant. So this 0.12 cannot be multiplied with 100% of your mass. You have to, the program will multiply with 50% of the mass, and also, but it is not directly multiplied. There is the formulas, and also for higher modes, let's say 2 seconds. So it will. This is 0.3 g. So 0.3 g will multiply with the 30% of the mass. So for each mode, it will consider it will calculate the base shear for each mode based on the participating of the class. And then finally you will get the base year for each mode. And then it will sum by the modal combination rule, CQC or SRSS. Then you will get the final base year, final response of the building. Okay, but one thing is this. Okay, this one is a factor of G. Okay, so you are getting the base year is the elastic base year. This base year is not divided by R value, because here we just specify the factors without R. Okay, so from response spectrum analysis, you are getting the base year, you are getting the elastic base year. Okay, but equivalent static analysis, you are getting the inelastic base year, which is already divided by R or minimum requirement according to the code. Okay, so when you design, you cannot design this response spectrum results directly. Your number size will be very big. So you have to scale down the response spectrum analysis results to equivalent static base year and then design it. Okay, so that one we call it scaling the results of the response spectrum. Okay, so I will explain you how to scale the response spectrum results in details in the next lecture, next week, because that one it takes time, and also important for the tall building. Because tall building we cannot use equivalent static at all. We have to rely on the dynamic analysis. Okay. So this is for the function, and next week I will tell you for the defining of the response spectrum cases, how to scale the response spectrum results. I might explain before briefly, but next week I will explain you in details. Because if your scale factor is wrong, everything will be, the entire design will be wrong. This is important. Okay. Any question?